Great to see you here again. In the previous video, we were looking into the Chinese remainder theorem. I already told you that the Chinese remainder theorem is very important when we are doing arithmetic with large integers. And now we're going to look deeper into that. This session will be about the computer arithmetic with large numbers. And we were going to base this, we're going to use this or explain this using the Chinese remainder theorem. Now, when we do arithmetic with large numbers, we already spoke about this, because when we look at the different elements, when we look at the different possibilities, we have to take into account the fact that when we are working with large integers, we may end up with a memory overflow in the computer. And memory overflows are things we don't like, because basically what happens here is that the program stops and we cannot continue. And of course, we will be working with large integers in many applications, so we have to find a way how to do these calculations. Now, modular arithmetic is very useful when we look at those calculations, when we are doing calculations with numbers that normally exceed the limitations of the machine. And this is a very interesting application that we will be describing in the following slides and in the remainder of this video. We can in fact express a number A by what we call an n-tuple consisting of its remainders upon division by different moduli. Now, the n-tuple, it depends. When we have two moduli, we have a two-tuple, a three-tuple, and a four-tuple, and so on. Now, let's look at the different moduli, m1, m2, up to mn, which are pairwise relative prime moduli, and m is their product. Now, what we can do is to represent the integer by those moduli. So we can replace it by a moduli m1, a modulo m2, a modulus mn. So basically this is what we do. We are going to represent the number by the n moduli. When we look at non-negative integers below 20, we look at them and we want to know what we can do when we want to know the ordered pairs composed of the remainders by division by 2, 3, and 4. So we want to know how will we represent those non-negative integers using this method. So we can represent in this case the numbers by 3 tuples, and the 3 tuples are ai modulus 2, ai modulus 3, and ai modulus 4. And the AIs are from 0 till 20 not included. Now we have this in the table, so when we look at 0, for example, 0 modulus 2 is 0, 0 modulus 3 is 0, 0 modulus 4 is 0. We can do that for all of them. When I look at 1 modulus 2 is 1, 1 modulus 3 is 1, modulus 1 modulus 4 is also 1, and we can continue. Let's take another example. For example, 7. 7 modulus 2, we can say this is 3 times 2 plus 1, so 7 modulus 2 is 1. 7 modulus 3 is also 1, and then 7 modulus 4 is 3. So we have the 3-tuple 1, 1, 3. Let's have a look at 18. 18 modulus 2 is 0 because we can divide 18 by 2. We can also divide 18 by 3, so we have a second value of 0. And then 18 divided by 4, we have a remainder of 2. So the 3-tuple for this number for 18 is 0, 0, 2. You can apply the same with all these numbers. It's a good exercise to compare all of them and see that you find the same results. Now, what to do with large numbers. Let's have a look. We've seen what the principle is, how we can represent a number as an n-tuple, and now let's have a look what happens with large numbers. Now we look at different moduli. We look at m1 up to mn. We look at different moduli that we can find. We have every, let's say, of those moduli is an integer greater than 2, and they are pairwise relatively prime. So we know that the greatest common divisor of mi and mj is equal to 1 for all I not equal to j. After selecting the moduli, we can write each integer we want to conduct the operation on as an n-tuple, as n-tuples composed of the remainders of that integer upon division by the modulus. So we're going to create that n-tuple. Now what we find here is a system of n congruences modulo mi, and we have to solve the system so that we find the result, and the result that complies with the system is in fact the outcome of the operation. So basically, when it's a multiplication, we will find the outcome of the multiplication, and when it's an addition, we will find the outcome of the addition. Now, there are two main advantages of these systems. We can do multiplications or operations on integers that are possible with using this method, which normally cannot be done on a computer. Now, what's also very interesting is that the operations or the calculations can be done in parallel, so it will save a lot of time because some of these elements are always the same. So we will see when we do an exercise, when we look at a number of the parameters, once we have the main values, we can in fact find a solution very easily. Now let's have a look of finding the n-tuple, first of the thing that we want to do. Now we will reduce the calculation of large integers to computations with integers smaller than 100, and we use their remainders moduli pairwise relatively prime integers less than 100. So the first one is 99, the second one is 98, then we have 97. 96 is not possible because they have let's say a divisor in common with 99. So the next one is 95. Basically, we have those four moduli that we are going to use to do the calculation. Now, by this Chinese theorem, we know that m is 99 times 98 times 97 times 95, which gives us 89,403,913 as a product. Based on this, we can represent each integer as a fourth tuple by its remainders when divided by those four moduli. So for the number that we choose, 256,342, we can say that it can be represented by the fourth tuple 31, 72, 68, and 32. And we find that by considering 256,342 divided by 99, and we find that the remainder is 31. So we do that for the different numbers. For 99, we find the remainder is 31. For 98, we find it 72. For 97, it's 68. And for 95, it is 32. Hence, we find the fourth tuple, 31, 72, 68, and 32. So that's the first step in the operations. The next thing that we have to do is we're going to add, for example, two large integers. And we want to add the integers 256,342 with 521,436. So basically what we have to do, we have the first 4 tuple we already found in the previous video, which is 31, 72, 68, and 32. We can find in a similar way the 4 tuple for 521,436, which leads to 3, 76, 61, and 76. Now, in order to add the operation, we conduct the addition on the 4 tuples. So we find 31, 72, 68, 32 plus 3, 76, 61, and 76. So 31 and 3 is 34. 72 plus 76 is 148. 68 plus 61 is 129. And we have 32 plus 76 is 108. So we basically what we have, or what we represent in the 4 tuple, is 34 modulus 99. So 34 is smaller than 99, so that's okay. 148 modulus 98. So basically 148 is larger than 98. So we can replace this by 50 modulus 98. 129 modulus 97 is also larger than 97, so we can replace this by 32 modulus 97, and we just subtract 97 from 129. We do the same for 108 modulus 95, and basically we find a 4 tuple which is 34, 50, 32, and 13. Basically, this leads to a set of linear congruences. So we have x is congruent with 34 modulus 99, x is congruent with 50 modulus 98, x is congruent with 32 modulus 97, and x is congruent with 13 modulus 95. And now we have to resolve this system. So when we resolve this, we use the Chinese remainder theorem. And we know that capital M is the product of the 4 moduli, which is, in our case, 89,403,930. We already calculated that in the previous slides. We can find capital M index 1, which is capital M divided by M1, which is 903,070. Capital M index 2 is 912,285. We find it by dividing capital M by M2, and so on. And we find capital M index 3 is 921,690. And finally, capital M4 is equal to 941 and 94. Based on this, we can write that 903,070 times x1 is congruent with 1 modulus 99. We can also write for the second variable x2 that it's 912,285 times x2 is congruent with 1 modulus 98. We have 921,690 times x3 is congruent with 1 modulus 97. And the last one, 941 and 94. We times x index 4 is congruent with 1 modulus 95. So basically these are the different equations that we find here following the steps of the Chinese remainder theorem. The next step is in fact the identification of the x index I value. Now how do we find x index 1? And we will repeat the same for x2, x3, and x4, but we're going to look at it in detail for x1. So basically we have 903,070 times x1 is congruent with 1 modulus 99. And we can find that this is in fact the same as x1 is congruent with 37 modulus 99. Now, how do we get there? Basically, what we have in the first part is that 99 divides 903,070 times x1 minus 1. So basically here we can find x1. And when we look at a table, when we put this in Excel, we can do the calculation for different values of x1. And when x1 is 36, we find that x1 times m1 is 325,10519. And we see when we divide this by m1, it doesn't give us an integer. And we can see that there is a difference. So basically, 36 is not a solution here. 38 the same. Basically, 37 leads to a division that gives an integer. So basically, the remainder is 0, which means that 99 divides 903,070 times 37 minus 1. And this is, in fact, the final result, that x1 is congruent with 37 modulus 99. We do that for all the different elements, so you can easily write that or make that calculation in Excel. And we do that for all the linear congruences. So we find for x2 is congruent with 33 modulus 98. For x3 is congruent with 24 modulus 97, and x4 is congruent with 4 modulus 95. So we can find x here. X is the sum of all those multiplications, xi multiplied with capital MIAI. And we find here the number here, it's 3,398,127,118, which is basically a solution. So what we can say, that we find here 3,398,127,118 modulus 89,403,930. We can say that this is 38 times m, capital M, plus the remainder is 777,778, which basically says that x is congruent with 777,778 modulus capital M, which means that the 770,778 is the addition of those two numbers. And since we have chosen rather small numbers here, we can easily prove this by simple addition. And you will see that the result is exactly the same. Now that was about the things I wanted to show you related to the Chinese remainder theorem and how we can use the Chinese remainder theorem to do operations on large integers without exceeding the capacity of the computer. And the main element here is that we don't want to have any overflows in the memory. That would be a real disaster for the program. So modular arithmetic using the Chinese remainder theorem is very interesting, but we still have some other interesting stuff to discuss here. One of those is Fermat's little theorem, which is also very useful when we are looking at prime numbers and other elements related to number theory. You're doing a great job. It's not always easy, and you can easily make errors doing these calculations, but I'm sure you're getting through it. Anyway, you can review everything every time you want. And of course, you're doing a great job, and I'm looking forward to seeing you in the next video. Thank you, and bye-bye.